shadow so means we need to hurry up and they have overcome this hurdle. Yeah, it doesn't seem because there also have other errors in that case. Yeah, there's another computer.
Okay, thanks everyone for staying to the last talk. So we're very happy to have Hongrui Chen from Stanford to talk about quantitative sampling to randomized samples.
Thanks for the introduction. And I will talk about our recent work on quantitative sampling algorithms through randomized method. So this is a joint work with Bo and Li and Jianfeng Lu and Lexin. So they are all here, so feel free to ask questions. So this talk is still about quantitative sampling. So this is the last talk in the workshop, so I don't need to explain the background again. So basically we want to prepare the thermostat for a given Hamiltonian. And there are various approaches for this. And in this talk, I will only focus on the linear blend-based approach. So we have a linear blend equation as this form. And I don't have coherent term here because we don't need it in this talk. And our goal is to construct a linear blending such that it satisfies the following three conditions. The first, we should have a unique stationary state that is the thermostat we want. And this ensures that our dynamic can converge to the correct state. Second, we want to have an efficient quantum simulation algorithm to implement the dynamic. And third, the blending should have a polynomial mixing time so that we can simulate the dynamic until the convergence. So for these three conditions, the first two conditions are actually perfectly addressed in the past 2 years by a series of works from like Andreas Green and Hongrui Chen, and also the work by Ding and Bo and Li. So basically for Hamiltonian, we already know how to design a linear blending equation such that the linear blending equation can convert to the correct state and also have a efficient algorithm implementation. But for the third condition, the mixing time is much more challenging. And as we discussed in this workshop, there are only a few examples that we can work out. And for example, in the commuting case, we already have some understanding on the mixing time. And also for non-commuting case, we only have some result for local and high temperature case. So this part is much more challenging. And in this talk, I will also address this problem. And I will give some more examples where the quantitative sampling can be efficient. This will expand the literature from a different perspective. So our motivation is that most of existing work only focus on the local or quiescent jump operators. But for some systems that is more challenging, like a system with a strong correlation, maybe the local jump operators may not be sufficient to ensure the efficient convergence. So the question is, can we use the global jump operators to enhance the thermalization? But the problem is, in general, there are actually exponential matrices of global jump operators. So how can we choose from them? There are actually one example that is a 2D Toyoko case, and it has been discussed in Zhijian's talk. So for 2D Toyoko case, we can use the symmetries of the system to design some global jumps. And it has been shown that the global jump based on the symmetries will help the thermalization of the dynamics. But this is because in 2D Toyoko code, we have perfect knowledge about the toric code, and we know where is the low range state. We know what is the symmetries of the system, so we can design the global jump operator based on our knowledge about the system. But in general, if we don't have sufficient prior information about the system, how can we do global jumps? So this paper will take one step to this, and our idea is very simple. Just we can randomly sample from the global jump operators. So I will talk about our new quantum keep sampling algorithm based on the idea of randomly sample from global jump operators. And I will first talk about our construction of the blend equation. And this construction will be based on the random enricher design. And then I will talk about how to implement the dynamic on the quantum computer. And also the maybe more interesting part is the mixing time. And we can give some more examples where the quantum keep sampling can be efficient. So our construction is based on some randomly coupling operator. So we want a random harmonization matrix A such that it satisfies this property. So basically this means for different entries of the harmonization operator, the correlation between them will be 0. But for each entry, the variance will be of order 1/n. Here, n is the dimension of the Hilbert space, and this is used for a appropriate normalization. So this coupling operator seems very unphysical. So because the Hilbert dimension is exponentially large, so we want the correlation is exactly 0. This is non-physical, but we can actually do this on quantum computer. So this may be the case where the quantum computer is more powerful than the nature. So and it may help us to design some algorithm. Our construction will be based on the unitary design. So we write the random operator as UDU dagger. Here U is the unitary design. And in some recent work, it has been shown that the unitary design can be realized by a circuit with log depths, depending on the statement size. So it's actually efficiently constructed on the quantum computer. And we also have a diagonal random operator in D in the construction. And here D is a diagonal random operator. And by diagonal, I mean on a computational basis, because we have the unitary design, so it's actually independent of the basis. So and each entry in a diagonal operator will be a random phase of +1 or -1. And this can be realized by a tensor product of poly Z rotation. So basically, we have independent binary variables on each side, and if this variable is 1, we do a Z rotation, and if it's 0, we just do nothing. So overall, this random harmonization operator can be constructed by this unitary design and the diagonal operator, and it can be realized in the quantum computer.
Why are the diagonal elements dependent? I feel like, so if you do it this way, then half of the eigenvalues are 1, half the eigenvalues are -1, so they're definitely not independent.
So what?
Like the way you construct E, like for poly Z string, unless it's entirely identical.
So you imagine you suppose I flip one. Suppose I flip one Z rotation on one side.
Yeah, but when you tensor with a Z matrix, it doesn't flip one.
It's like it's like if you consider a uniform distribution on a hypercube, it's just equal to the tensor product of binary variable.
But still, like if each entry is like independent +1 or -1, then like there's no reason for the whole thing to be traceless, right? Like
actually, this is up to a phase factor. So for the first entry, it must be 1. So but other entries are +1 as well.
sorry, maybe we can talk about that.
Question? So here, do you need the fully random string, or can you use like a pseudo-random string, like a k-wise independent? I mean, for the P1 to Pn, here you say they are fully independent binary random variable. Can you replace it or weaker the randomness assumption to be like a k-wise or forward?
Maybe you can do this, but it's just a classical random variable, so it doesn't matter. Using this random coupling operator, we will construct the depth generator, and we have discussed this a lot of time in this workshop. So the depth generator is given by the jump operators of a depth generator is given by some Born frequency mode of the coupling operator A, and each mode is given by the Fourier transform of the Heisenberg evolution of A. And we also have a weight function to ensure the detailed balance condition. An interesting thing is that in the case of a random coupling operator, the depth generator is equivalent to integral form reformulation. This integral form is constructed by this works and also from these people, and they use the integral form to construct the jump operator for general quantum Gibbs sampling task. And each jump operator is given by integral of the Heisenberg evolution of the coupling operator and with the weight function f. And if we choose the weight function to such that the Fourier transform f is match the weight function we want to ensure the detailed balance, it will give the detailed balance condition. But in general, this construction does not ensure this construction is not enough, because we like we discussed in the Andrew's talk, there should be an additional coherent term to ensure detailed balance. But in our case, because we use the random coupling operator, we don't need the coherent term, and just this jump operator is enough, and they are just equivalent to the construction from Davis generator. So this is one of the advantages of using random coupling operator. We can directly simulate this integral form, and it can help us to simplify the algorithm.
Yeah, so when you say this is a Davis generator, so you can prove it satisfies the GNS detail balance condition?
Yes. So this is a KMS construction in general, but for the case of random coupling operator, they are just equivalent. So now I will discuss how to implement it on a quantum computer. And basically, we will use the randomness method, and it's how the randomness method in our title comes in. So let's first study a much more general framework for the Lindblad simulation task. So suppose we have a set of invariant LA, and each LA has some simple form, like it only includes a single jump operator. And this ensemble can be arbitrarily large, maybe exponentially large, or even infinite large. And we have a operator bar L that is an average over all the invariants. And then we want to simulate the Lindblad of bar L. And this can be done by the random product approximation. The idea is that we can decompose the evolution of bar L to many steps of short step evolution. And for each step, we randomly sample a Li from the ensemble, and then run a short time evolution of this Li. So we can repeat this for m steps. And if we consider a fixed evolution time and take the step size to go to 0, this random product approximation will convert to the exact evolution of into T bar L. So this idea is motivated by the Q-drift method in the Hamiltonian simulation context. Here we just want to, and this method is of independent interest for the simulation of some physical system. But here I will just focus on the application in quantum Gibbs sampling. So basically, using this method, we can handle a large number of quantum jump operators, and it might be helpful for trip sampling. So now we reduce the problem of simulate an ensemble operator to simulate a single operator for a short time. Each operator LA is given by a single jump operator. And this allows us to do some very simple implementation in each step. So for example, we can use the dilation-based method. It's also discussed in Chen Tao's talk. So the idea is very simple. We can approximate the linear evolution by a short-time evolution of Hamiltonian. This Hamiltonian is a dilated version of the jump operator. So because we only have one jump operator, so this dilated Hamiltonian, so we only need one Siena qubit to do this, and we can use the Hamiltonian evolution on the system coupled with this Siena qubit. And this will induce a second-order approximation of the original linear evolution. So this gives us the one-step implementation. So overall, our algorithm will be like, for each step, we sample a linear blending and couple with the Siena and use the Hamiltonian evolution. And then we resample in the blending and refresh the Siena and do this again. And by taking the interaction, we will get a evolution of the linear blending. So I will give a brief discussion about the analysis of our algorithm. So in particular, we want to understand how many steps are required to achieve a reasonable error for the algorithm. Suppose we have so first we need some definition. So we have f tau that denotes the single-step implementation of the jump operator. And if we use the dilation-based method, this is the second-order approximation. We'll also consider the average channel, that is the mixture of all the random realization of the algorithm. So for each step, the jump operators are randomly sampled, and in the average channel, we just take the average over all the random realization. This will describe how the algorithm works.
One question. So why you say it's a second order? Because of the consequence.
So for example, if you use the dilation-based method, this is second order.
You prefer to say it's a one-step error, right? So
yeah, I mean the one-step error is second order.
Oh, okay, good.
What we want to do is to measure the difference between the average channel and the exact evolution. So our theory is that so suppose the norm of the operator is bounded, and we want to simulate the linear blending barrier. So, sorry, this should be expectation, not this style. So, and the result is that if we want the error between the average channel and the exact evolution to be at most epsilon, the required number of steps is lambda squared t squared over epsilon. So notably, this will not be dependent on the number of jump operators. So, but if we naively using first order shorter, it will have some linear dependence on the number of jump operator if we use some worst case analysis. And of course, this algorithm is suboptimal because, as we discussed in Chen Tao's talk, the optimal dependency on t should be linear and on epsilon should be log. But here we don't want to compare the complexity with the most fancy method. We just want to say that we can use the simple method to simulate a linear equation with a large number of jump operators, and it will be very useful in our algorithm. So this algorithm will avoid some complex oracles or control circuits. So we only use Hamiltonian simulation on a system coupled with ICR. So now we discuss how to use the randomized method to simulate the equation we construct. recall that our construction has this integral form. So it's an expression over all the jump operators, and each jump operator is given by which is the integral of the Heisenberg evolution. And each A is a random Hermitian matrix. Using the randomness method, we can reduce the problem to just simulate a single Ka for a short time. And each single step simulation can be implemented by the dilation-based method. And the idea is very similar to the work by Ding and Anthony. This work is for ground state preparation, but their construction is similar to in this case. And they have provided some very detailed discussion on the algorithm implementation and the numerical analysis. Here I will just outline the idea. So for each single step implementation, we can use the dilation method to reduce it to the Hamiltonian simulation problem for the dilated Hamiltonian. And then we evaluate the integral by quadrature and then do trivialization. Then we will reduce the problem to simulate a single term in the quadrature. And we will get our rate. And each step is like this slide. And so on the left, there are three terms on the right-hand side. So for the first and the third term is just is just to implement a usual design and some Hamiltonian simulation. And for the middle term, this is recall that D is a diagonal matrix that just given by some Pauli Z rotations. And the sigma L is some Pauli. And so this is just a Hamiltonian evolution of Pauli string. And it can be implemented efficiently. In particular, we can do some Pauli rotation to rotate each Pauli to the Z basis, and then it's just a dialog thing, and there are some efficient methods to do this. So this is a algorithm implementation, and now I will turn to the most interesting part, is the mixing time of the dynamic. By the algorithm implementation and the mixing time will will lead to some result on expression mixing for some class of Hamiltonian. So the mixing analysis will be based on this observation. So it's that the evolution of the system can be decoupled to the diagonal term and the non-diagonal terms. And this is because we have the randomness structure. So many of the terms are cancelled out. So the only thing remains things on the diagonal and non-diagonal. So on the diagonal terms, we can show that the dynamic will be reduced to a classical Motrapoli-Hastings algorithm.
N is the Hilbert space dimension.
Yes. So this comes from our construction, because we use the usual design, so everything is spread out in a whole Hilbert space. So there is a factor of 1 over n. This is the classical Motrapoli-Hastings algorithm, and so this is
Never.
not never, but some cases it can be polynomial.
N is the number of qubits, right?
No.
Yeah. So let's say.
But the n is exponential large, but there are many terms in the summation. There is some hope. So this is the continuous Markov chain. I'll describe the Motrapoli-Hastings algorithm. So, but its discrete counterpart maybe more easier to understand. It's like it follows from the proposal and rejection procedure. So in the proposal step, we uniformly sample from or the so this is a random work on the state on the space of all eigenstates. So So from each from any eigenstate in the proposal part, we randomly sample another eigenstate. It's a uniform proposal over the whole spectrum. And in the rejection part, if the proposal has a lower energy compared to the current state, we accept it. And if the proposal has a higher energy, we reject it with probability to the beta times the energy difference. So this is just a classical algorithm that using a uniform proposal and a rejection. Maybe the uniform proposal is not the most desired one, but here we can avoid it because we use the usual design, and without it we can reduce the problem to a classical Markov chain. And the things happening in the non-diagonal terms are more simple. It's just the exponential decay on every term. So to understand the decay on the diagonal term, we only need to quantify what is the decaying rate. So all things are so now everything are classical. So we have a random walk on the spectrum, the exponential decay on the non-diagonal terms. And so the mixing time will only depend on the information on the spectrum. So our mixing time result is that we show that the mixing time is determined by the quantity by R beta, and R beta will quantify the ratio of states within an energy window that is just above the ground state. This is the definition. So number minimum is the ground state, the energy, and we want to consider an energy window just near that ground state energy, and the length is 1 over beta. And this quantity will give us how many energy states, how many eigenstates are there in the energy window. So there is still a 1 over n factors, but if so what we want is the ratio to be not exponentially small. So the spectral gap of the dynamic will be bounded below by this quantity R beta. So if the quantity R beta is not extremely small, our algorithm will give a fast convergence. So one example of if our algorithm will work is that if the spectral densities approximately satisfy the semicircle law. So this is in the case of the spectrum of a system is described by some random matrix theory like Julian ensemble. In this case, the quantity R beta will have the polynomial dependence on the inverse temperature, and will have a fast convergence as long as the inverse temperature is not exponentially large. So there are actually one probable example for this, and this example is picked from also a work from Anthony, like several years ago. They consider the problem of prepare ground state or prepare the low energy state for some Hamiltonian. And they use this example in their paper. So this example is the random sparse polystring. That is, each term is a random polystring on the state on each side, and we have a random coefficients. And the number of the sum is m, and m should be sufficiently large, but not so large. We need to m is larger than this polynomial, but not exponential. So in this case, we will have that with high probability the quantity R beta will be of order beta to the minus 3 over 2. So this will be a polynomial dependence on the inverse temperature. In this case, we will have an efficient mixing algorithm. There are some connections with the quantum chaos. So in literature of quantum chaos, it is conjectured that the level spacing statistics of chaotic Hamiltonian is predicted by some random matrix theory. So it's like it's like the GUE ensemble, and so the spectrum will be like semicircle law. But the connection will be tricky. So we can claim some rigorous result on this. In conclusion, what I have proved is that we have provided a new class of Hamiltonian where the task of preparing surfaces is quantum easy. So the Hamiltonian should satisfy the two conditions. First, we have a efficient simulation algorithm for the Hamiltonian, because we will use this in the algorithm. And second, it have a non-negative low energy density. That means the quantity R beta is not exponentially small. So this actually give a mathematically this actually give a very elegant condition on what kind of thermostat can be prepared. But physically, this may not be very interesting because it excludes many interesting cases. But in the future work, it will be maybe more interesting to consider some combination of random global jumps and local jump operators. Maybe we can combine the usual design and the local jump operators, and it may work for more cases. And it's also interesting to consider some usual design on the subspace instead of the whole space to get some more interesting mixing result. So this is the end of the talk.
Some questions.
Yeah. So intuitively, can you explain why you need set R beta H to be large so that you can have fast mixing? It seems like if R beta H is large, then a lot of your eigen energies will just be very, very small and
yes.
Together.
So it's like because there is a random walk on the spectrum. So and the mixed time of the random walk will just depends on how the spectrum will distribute on the energy spectrum. So if the energy domain, the spectrum is very sparse, because our proposal is uniform. So we at each step we randomly pick a eigenstate. So you imagine the ground state preparation task. So in that case, we push the state to the energy state, but because in each step our proposal is uniform. So if in the low energy region there are just exponentially small states, we may never go into this region.
If you apply this to SYK.
Actually, I assume this can be applied for XYK, but this is hopeless after I heard the talk from Anthony. so because the SYK, the spectrum of SYK model is actually not like semicircle. So the physical prediction is that the level space statistics is predicted by semicircle law. That means the distribution of this, we consider the energy difference between two energies, and the distribution of this quantity will be like the distribution of semicircle law. But this is actually a local quantity, so you have to consider so you only have some information locally on the spectral domain. So actually, for the SYK model, the spectrum is also like a Gaussian, not like a semicircle law. So the behavior of
even for constant beta, you have too few states. Right.
So we only have this information about the level spin statistic, not about the whole spectrum.
Well, if no more questions, thank Hongrui again. Thank